Okay. So I guess while we wait, are there any questions from last time? I also wanted to emphasize that if you have any question, I'll be around this afternoon, so please find me and you can ask me any question. Maybe you don't dare to ask in front of everybody. Please dare to ask in front of everybody, because maybe everybody will benefit from your question.
Why don't we go ahead and get started?
Okay, so we'll get started. So last time we discussed a type of model that where these melonic diagrams were dominating. SYK was an example. There were other tensor models that have the same features. And these models are roughly as easy to solve as ON models, perhaps a little more complicated, but they have a very similar structure. And then we concentrated on one particular example, which was this example in D equal to 1, or quantum mechanics of fermions, the so-called SYK model. And this model is trivial in the ultraviolet, and at low energies it develops, or some low but not extremely low energies, it develops a nearly scale invariant regime. And in that nearly scale invariant regime, the correlator we saw that the 2-point function, so G, which is essentially the fermion 2-point function, is proportional to 1 over the difference of times, d1 minus d2 to the power delta. So what's important here is that it's some scaling, has a scaling form. One can compute the delta. This depends a bit more on some details of the model. In the simplest model it's 1/4, but there are other versions. And then we can insert the solution in the expression for the free energy. And then we find that is proportional to n with a factor. There is a diversion factor we cannot calculate using this, but it's just the ground state energy. And then there is an interesting term, which is what's sometimes called the zero temperature entropy. Or now, okay, so that's the result obtained to leading order in n. Now, you might say, well, this model has a scaling symmetry, and in higher dimensions we're used to the fact that if theory has scaling symmetry, it also has conformal symmetry. Okay, so conformal symmetries are coordinate transformations that preserve the metric up to an overall scale in the metric. And in fact, there are some theorems saying that if you have a quantum field theory in a certain number of dimensions and so on in 2 or higher dimensions, well, I guess it was proven only in some, not in all dimensions, but you can prove that then you also will have the conformal symmetry. Now in this case, conformal symmetry is would be basically the set of all coordinate transformations. So it would be any reparametrization from t to f of t. Okay. So the question is where the theory is invariant under all these transformations. Okay. Now, of course, the full theory will not be invariant. So the question is really where the low energy theory is invariant, right? So because we had a non-trivial energy flow, so the full expression for the 2-point function was not scale invariant. Only the low energy, some appropriate low energy expression is scale invariant. So we had, so as a check, so if whether we have this invariance, we can look at the equations for the model. Recall that we wrote many times the equations, and the equations had the form dt of g, let's say t and t prime, minus integral dt double prime of sigma of t double prime g of t double prime t prime equal to delta of t minus t prime. Okay, this was one of the equations, and then there was another equation that was saying that sigma was equal to g cubed, right? So we could just directly here put g cubed g cubed t prime t double prime. Okay, and we are asking whether this expression is conformal invariant under arbitrary time reparametrizations. Okay, So we now at low energies we had, so it's actually not invariant, but at low energies we were neglecting this term. So really the question is whether after we neglect this term and we solve the low energy equations that we had written before, recall we wrote this equation in Fourier space as a product of two functions in Fourier space. So this is the same expression in just coordinates, and it's simpler to see this transformation when you write it in time and in position. So the question is whether if we have some function g, and then we define a new function, let me call it gf, that depends on what this function g is, and also depends on the function, which is defined to be, we're going to define it to be f. So this is the definition of the transformation to the power delta, and then we take the old function, but we evaluate it at these times. Okay. So this is a transformation in the space of functions of two variables. Given one function of two variables and one function of one variable, we generate a new function of two variables. Okay, that depends on that function f of one variable that we had. Okay, and so you can check that if we put this in this expression, then in this t double prime factor, we'll get an f prime to the 4 delta, 3 from here and 1 from here. But then we also get an f prime here from the change. So this is an integral over dt t double prime, but when we write it in terms of an integral over f, right? We can rewrite it in terms of an integral over f, and then that absorbs the factor here that we had. In other words, yeah. So that's good. And then we are left with some other factors that again, after we use the equation of motion for the original function, after we use the original functions obeys the equation of motion, then we find that the new function also obeys the equation of motion. So you can check by replacing here that it indeed is, I won't go through it in detail, but it is invariant. Okay, very good. Now, so this is a symmetry of the equations. We could also have stated this at the level of the action. It might be a little confusing to check the invariance of the determinant, but it is invariant. So that's why we did this way. But we can ask whether this function itself is invariant. So this function is not invariant. So this is an invariance of the equations, but the solution of that particular solution is not invariant. And if we apply that to this solution, let me call this let's say the conformal solution. Let me put a C here. So we can apply this transformation to that conformal solution, and we get some functions, which it's really applying this transformation. I'm just going to write it explicitly so that it's very clear what we are talking about. Okay, so starting from the original solution there, we get a family of functions of two variables, which is this particular family, right? This is explicitly what we are talking about, depends on f. And this is not the same as that, except for some very special f's. So there are some special f's for which it is the same. So for example, if f is simply, let's say, lambda times t, right? Then there is a lambda factor here and a lambda square. So there's a lambda square in the numerator, lambda square in the denominator. It cancels. In that particular case, it is the same, right? But for a generic function, they are not the same. The particular functions for which they remains invariant is the SL2 transformations of the original expression. Okay. So at this level of analysis, what we have is that we have the space of functions. So imagine the space of functions of two variables, which is a very high dimensional space. Let me call them G. These are different dimensions in the space of G. And we have one particular function, which is the one we discussed over there, 1 over t, 1 minus t2. And then we have a bunch of other functions that we get from this one by applying this transformation, right? This transformation does not give a generic function of 2 variables. It gives a special function of 2 variables, okay? So it's like a lower dimensional subspace within the space of functions of 2 variables, okay? All these functions are solutions of the classical equations, okay? Of the low energy, of these low energy classical equations. So then at this level of analysis, we have a kind of Goldstone boson, which is a well, the symmetry is these reparametrizations that we are spontaneously breaking by choosing a particular solution, but all the other ones are equally good solutions of these low energy equations. Okay? So we have a manifold of solutions parameterized by f. So it's a very high dimensional manifold because f, of course, has many Fourier components. Okay. Good. Now the manifold is not all diffeomorphisms. So it's not all of the diffeomorphisms because there are some of them which so if you take an f and you change f by af plus b over cf plus d. So if we change f in this expression to a new f, let's say f tilde given by this expression, we'll get exactly the same function here, right? Due to the original SL2 invariance. So really the space of Goldstone bosons is parameterized by these diffeomorphisms divided by SL2. Okay, this is the group generating SL2 transformations. And this is as usual that the symmetry is not completely broken. There is an SL2 that survives, and so the space of Goldstone manifolds is G over H, where H is the group preserving the symmetries. Okay, now this whole thing it is arising in a computation where we're computing the functional integral of, we remember what we were doing. So we were doing some functional integral over G and sigma, and we had some action that depended on G and sigma. We found the minimum here, the equations for the minimum that gave us that function in this approximation. And now we found not only one, but we found the whole manifold, an infinite dimensional manifold parameterized by continuous variables. So this, in this approximation, will give us infinity once we integrate over this manifold. Okay. Okay. So now this is wrong because the original remember this was supposed to be exactly equal to a function where we were integrating over n Majorana fermions, so a Hilbert space which was manifestly finite. Okay. So we cannot get an infinity. So if we getting an infinity, we are doing something wrong. So what we are doing wrong is that these equations were an approximation. They were not the exact equations. We made an approximation, and so if this approximation was completely valid, then we would have this whole story. But this direction cannot be completely flat. There should be something that removes, that picks out a particular configuration within this set of possible configurations. Okay, so and this is a common situation when we analyze problems that maybe we first solve some part of the problem. So here it would be the integration of the modes orthogonal to this curve, right? So there is in the directions of the wall of the valley. So that gives us that can be done within this low energy approximation and gives answers which are exactly conformal invariant, the scale invariant. And then we'll have the integral along this direction that will live for last. Okay. I guess a simple example of something vaguely like this is imagine you have a pendulum made of ordinary matter, right? So then first you say, well, the interactions between the matter make a little spherical ball that is solved somehow, and this part is independent of the position of the pendulum. And then you have a piece in the action that depends on actually the position of the pendulum. Okay. And that part depends on on the angle, right? For example, it's not perfectly translation invariant, but there is some angle of the pendulum, and that part of the action can be computed without knowing the details of the matter that made the pendulum. Okay, but you are assuming that any interaction of the matters that made the pendulum is invariant under translations in space, and then there is a small thing that breaks those translations in space, which is the force of gravity. Okay. Good. So here we are going to make a similar approximation. That first we solve we solve using this Lagrange approximation the solution in the directions orthogonal to the valley, and now we have the space of solutions along the valley, and we'll try to find an action on this valley. Okay, so let's go back to our original expression for G, G conformal. And let's think of it as a function of the difference of time. So this is G of t, G of t, where t is the difference of the two times, and that function is some function that has is a power law of this kind, right? That is supposed to be a good description for low energy. So low energy corresponds to long times. Okay, so that's a good description of the solution here, but it's not supposed to be a good solution for very short times. In fact, this solution you can very easily check that is wrong for short times, because this expression, what is that expression? That expression is the product of the Majorana fermions, okay, at different times. So one at, let's say, 0, and there one at time t. Now what happens if we put the two times equal? Then we get the Majorana fermion squared, and that's just 1. And the average of that should be 1, okay? And this is infinite. So this is manifestly wrong. And so the correct answer is something where you start from, let's say 1 is up here, and then it curves down and matches to the long distance answer. And it differs from, the two curves differ at the distance, this distance here will be of order 1 over j, right? So that's the transition between the part where the correlator is essentially constant, independent of time, with 0 Hamiltonian, and then as time progresses, the Hamiltonian becomes more important, and the correlator, we're doing this, let's say, well, this is true both in Euclidean and Lorentzian time. It gets this operator starts growing, becomes some other operators, and the overlap with the original fermion becomes smaller. Okay. So what that is saying is that this whole discussion is a good approximation for when the two times are separate, are different, but not when the two times are very close to each other. So if we look at this functional integral, we would conclude that we just checked that when the two times are different, there is no action for f. Okay, there would not be any action for s. That's a symmetry of the action. But that symmetry of the action could be violated when the two times are close to each other. Right? And so that makes us think that the action for f should be a local action. So it should be an action that comes when the two times are close, and so we'll have a local action which is a local Lagrangian of f prime, and f double prime. So we'll imagine we have an action of this kind. I mean, this action comes from really the original G and sigma action, and this action can actually be derived explicitly from the G and sigma action. It's a long story that I will not go through, so I'm just trying to give you an idea for why we should have expected this answer. Okay. So there will be an overall factor of n, because it's simply an approximation of the original action, and now we would like to understand what it is. This should be an action that is defined on G over H, or by the group divided by SL2. So it should be defined here. Okay. That means that it should be invariant under this type of transformations, right? So whatever action we have there better be invariant under this type of transformations. And the idea is to write down the action that has the smallest number of derivatives that is invariant under those transformations. The answer to this problem is to say that this action is actually the Schwarzian of f of t comma t, which is just by definition a particular combination of derivatives that is invariant under those transformations. Okay. So this particular combination of derivatives has the property that is invariant under those transformations. Okay, so that's the argument. So now that we've found this expression, we could count the number of derivatives that it has. So this has basically two derivatives. So the f prime here cancels with the f, that one of the primes here. It has a net number of two derivatives. And there is one integration that sort of cancels one of the derivatives. So this whole thing here has dimensions of energy. And so there should be a coefficient here that by dimensional analysis can only be j, right? And the whole action will have some alpha s, some numerical constant in front that we have to calculate somehow by that this argument does not give you this constant, right? This constant, if you want to calculate it, you would have to start from the original action, including the derivative and so on, and find it. Okay, so you can go through the flow. You can find it numerically. We did find it in a paper, but anyway. So this is the derivation by essentially the symmetries of what this action could be. So the analog in the case of the pendulum is so you know that there is a minimum, and so the simplest thing it could be a harmonic oscillator around the minimum. Okay, so that's the simplest action for the pendulum fluctuations around the minimum. The actual pendulum is not exactly x squared, so you can it's a more complicated function. It's cosine of x minus 1 or something like this. So you're not getting the higher orders. You're only getting the smallest action by looking at the simplest term that could violate the symmetry. And this here we are looking again for the simplest term that violates the symmetry. Here the symmetry I'm talking about is the reparametrization symmetry. Okay, now so one use of this is to so this will look a little weird, but let me so let me just make a comment here that one use of this reparametrization symmetry might be to go between the infinite temperature between the zero temperature case, which would be that correlator, and the finite temperature situation. So that's like mapping the line to a circle, and so that is achieved if we take f, which is tangent of pi. I'm going to denote the physical time by u over beta. Okay, so u is the physical time of the quantum mechanics. And if we insert this into the expression in the top left corner of the blackboard there, we would find the finite temperature correlator, which follows again from conformal symmetry that has a form 1 over beta squared sine, well, let's call it beta pi u over beta, okay, to the 2 delta, proportional to. So we get sort of the finite temperature solution simply from the zero temperature one. This is not, yeah. This transformation becomes infinite at some times and so on, so it looks a little weird, but so you can check that this is a solution. So this is a solution of the finite temperature equations. Now, once you have these finite temperature equations, then again you can do reparametrizations of the circle. So it's useful to think of this as, for example, tangent of phi of u. Maybe there's a 1 over 2. Yeah, maybe over 2. Okay, so this is a circle with standard radius 2 pi, right? And so then sort of the action in this case, so times the integral over u, and then now we have the Schwarzian of tangent phi over 2 comma u. Now the reason this looks like I'm doing some trivial statements, but I wanted to write it this way so that now when we talk about reparametrization, so the reparametrizations that are actual zero modes of the problem, or are light modes, are reparametrizations which are maps from the circle to the circle. Okay, so we have maps from the circle to the same circle of the same that do not change the radius of the circle. So the diffeomorphisms of S1 divided by SL2 is a space of really truly zero modes. The reason we are not allowed to rescale beta, so I mean here of course you can rescale U, and that's a reparametrization, right? But those are not allowed because recall that there was this term in the action, this diversion term here, which would change if you make such a reparametrization, right? So first you fix beta, and then you do reparametrizations that fix the size of the circle. Okay, those are truly zero modes of this action. This is just a small technical detail. Anyway, so those are zero modes of the action, and you can I expressed it first starting that way, but you don't have to do that. You can just consider purely this group and consider the SL2 transformations that act on this action, and that again determines the form of the Schwarzian to be exactly this. This is exactly the same as the previous Schwarzian, so let me rewrite this. So this is equal to just the usual the Schwarzian defined previously, plus some term that involves a phi dot square with some coefficient, which I leave to you to compute as an exercise. Okay, some order 1 coefficient here. So that tangent, all it does, it gives this extra term here. Now the thermal solution corresponds to taking phi to be pi u over beta, and then you can insert this in here. This term contains second derivatives of phi, so that term does not contribute, and then you get a contribution from here, which goes like 1 over beta squared. There is an integral over u that goes from 0 to beta, so the total final contribution is a factor of 1 over beta. So now we have a new term in the formula for the partition function, so I'm going to return to this partition function that we had the first approximation here, and we are finding here a new term. Again, has an overall n multiplying because it's all of this comes from the classical action that has an alpha s, a number that I leave to you to compute, and a beta j. Okay. So so far we have this at this order. Okay. So this is a term in the entropy that is linear in the temperature. So we could call it alpha s t over s. And the fact that it's linear in the temperature is a consequence of this pattern of symmetry breaking that we are discussing. You can say it's a consequence of this conformal symmetry. Now naively, if you were told that you had a theory that had a fixed point, and then there is some perturbations away from this fixed point, some irrelevant deformations, well, the power could have been anything. Could be some irrelevant operator with any power. You might have thought that the power could be anything. But the fact that the power is precisely 1 came from this particular pattern of symmetry breaking. Now, unfortunately, there are other things that can give you also the same power. So if you are, let's say, a condensed matter theorist, and you are, well, or an experimentalist, and some theorist tells you, oh, you should find the temperature linear in the, an entropy linear in the temperature. Okay, so they would say, okay, this is very easy to get. Just a free Fermi liquid has this temperature, has this behavior, and so on. So this is not, does not characterize this uniquely, but it's certainly a prediction of this this story. And we'll see that the same pattern of symmetry breaking holds for near extremal black holes, and there indeed the entropy of all near extremal black holes is linear in the temperature. Okay, so now we'll do one more thing that can be done, and it is to ask the following question. So let's imagine that we were to compute 1 over n corrections of this action, right? So this is some action, so we computed the leading order expression. Let's still be at low energies, and let's compute the 1 over n correction. So 1 over n corrections, the first correction will come from integrating over g and sigma around the minimum, right? All of this we've done so far is classical physics, evaluating at the minimum, at the solution. Now we'll integrate around the minimum. And when we do that integration around the minimum, we can integrate in the orthogonal directions or in the directions along f. Okay. The integral in the orthogonal directions is finite, and not only is it finite, but it's also conformal invariant. So the whole expression here is conformal invariant. So we know what type of answer we expect. What we expect from those integrals in the perpendicular direction is again a constant, because it should be independent of j. There is no, so there will be some, let's say, S1. And we could even go to higher orders, and we find S2, etc., to various orders in the loop expansion of the g and sigma action. But the important point is that all of these corrections will not give us a correction to that is temperature dependent. Okay, so the conclusion is that all the part of the theory that is conformal invariant will give us a factor. Well, I'm going from now on drop this factor. So it will give us a factor which is e to the S0, the total entropy, and S0 will have an expansion. Will be a term of order n, a term of order 1, a term of order 1 over n, etc. And then we have to do the integral along this direction. But the integral along this direction, so that's the problem. So before discussing that, let me say once more what we are doing. So we are trying to do a functional integral over g and sigma, and we are going to split this functional integral into first an integral over f that we leave for last, and then an integral over the g and the sigma in the sort of perpendicular directions to f. Okay, so at each we move along f along that valley, we integrate along all the directions orthogonal to the valley, and then we leave the integration along the valley for last. Okay. So first we do this whole integral, and the idea is that that whole integral will leave us with a Schwarzian action which has some coefficient, 1 over some coupling constant, integral du Schwarzian fu. Okay, so that's what we are doing. And this g0, well, of course, is that prefactor that we had over there, right? It's a coefficient of the dimensions of time, right? So we could rescale this time coordinate from 0 to beta to be some rescale time that goes from 0 to. So this is a little better if we write it like tangent phi over 2, and then u, and then this u goes from 0 to 2 pi, so rescale u, and then this coefficient will be of the form n alpha s beta over j. So the dependence of whatever we do is on this parameter. In principle, this parameter here could have 1 over n corrections after we do the previous step, but everything depends on this overall scale that multiplies. Well, now it's dimensionless, overall dimensionless number that multiplies this Schwarzian action. When this number is large, we can use the classical approximation, and that's what we did over there, right? That's what we did when we looked at the classical solution that was linear in U. So that is valid when the temperatures are not too low. So very low temperatures means very large beta, and this becomes very small. Remember, yesterday we discussed that first we were going to consider temperatures that were much less than j and much bigger than j over n, right? That was to trust the classical limit. What we're going to do now is we're going to go to temperatures smaller than j over n, okay? So that we can do that if we can quantize this theory. So or in other words, do the functional integral of this theory. And this was done. It was done by Stanford and Witten, and there were also some previous papers doing it perhaps a little less formally by Braggart, Kamenev, and a third author I'm forgetting. So, and the final answer is 1 over beta, well, so here we have the classical answer, which was alpha s beta over j times some number that I'm not keeping track of. So this was the classical answer. This has the form of a one-loop correction, And what these people have shown is that there are no further corrections. So this action is very special. It's a very special theory that for which all the higher loop corrections vanish. And in fact, there are some tricks to rewrite this as a Liouville theory. So it's almost like a free field. And that kind of justifies, at least in a vague way, this expression. Okay, so the idea is that this is computing the partition function, and we can go beyond this regime, presumably at least to all orders in perturbation theory. Yeah.
You mentioned one local correction is enough. So it's sort of like localization.
Yes. Indeed, the technique that was used by Stanford and Witten was a technique of localization that uses localization. Yeah. So the idea is that they are using a technique. They are using Dussert-Heckman theorem, which is a formula that says that if you have an integral over some phase space, let's say some integral over some phase space M of some function h, which is the generator of a U1 symmetry, then yes. Yeah. And that's a symmetry sort of generated by the Schwarzian. And so you have to define so this is some space that has no structure. It's not obviously a symplectic space. So you first define a symplectic form on this space, and then the Schwarzian itself creates this U1 symmetry. Anyway, so so I'm not explaining the details of why this is true, but you can believe that it is true. And here the crucial, I think the crucial conceptual idea was the idea that just the symmetries give us that action, and then we somehow solve for the action. Right? So the equivalent step in the case of a harmonic oscillator or something similar is, or the pendulum, would be to say, imagine I want to determine the energy levels of the pendulum. Well, there will be a bunch of energy levels that come from the matter. There's a huge number that come from the matter, and so on. But those do not depend on the gravitational Newton constant. And then there is the position. There is the term that depends on the harmonic oscillator of the position that depends on the Newton constant and the length of the string that joins the pendulum. And so we are computing those terms. We're not computing the energy levels of the matter and so on. So similarly here, there are a bunch of states and so on that come from the conformal part that we're not computing, but we're computing this temperature-dependent part. Okay, good. Let me see. Okay, so we said this is an integral along this valley, that we already said, and we got the final answer. Okay, there is one more thing one can do, which is to do a Laplace transform of this expression. So maybe I should rewrite it again so that it's more clear what we're doing. So we neglect the ground state energy. We have an entropy, and then we have a term that goes like 1 over beta j to the 3/2 times e to the n. I mean, there is factors of n here which could be absorbed here, and n over beta j times some number. So we had this expression. And now we can think of this as arising from some density of states, right? So this is just the definition of rho e. So we are just saying we're going to try to find the rho e that matches that calculation that we did by doing the Euclidean functional integral. Okay? And after you do this, so you find that rho e is equal to some constants, so that include the factor of e to the s0, then some other numbers, and sine hyperbolic of square root of e times again some constants. So there will be a factor of j and n and so on. I leave to you to compute the constants. So there are some constants that, of course, depend on the constants that appear here in this exponential. And a simple way to determine the constants is to go to large E, where this becomes an e to the square root of e. And then the relationship between the coefficients here are those of given by classical thermodynamic relationship, right, between the log of the partition function and the energy. Okay. So this defines a kind of density of states that we computed by using this these patterns of symmetry. So all of this just follows from the realization of the symmetry. So that's why I'm trying to emphasize this point. And remember that when we talked about the density of states of the SYK model, so we drew some formula roughly like this, right? So now we have exactly how this goes here. It goes like a square root in the beginning, and then it starts growing exponentially. Okay, so that's the shape, and then this is the shape near the endpoint. Then it grows, then it's not sinh anymore, and then it goes down again. Okay, so that's the formula. There is an overall factor which is exponential in n, which is this factor. So this is exponential in n. Okay, because it starts like coefficient times n plus and so on. Okay. Now you should compare this computation. Notice that in this we did not do this computation by finding all the microstates of the SYK model and then finding the density of states, right? So we did the computation by using a Euclidean method of we start with the trace of e to the minus beta h. We translate into the g and sigma variables. Those g and sigma variables are vaguely similar to what we have in ADS-CFT when we talk about the bulk interior, right? There is n appears only as a coupling constant. And then the computation that we did is conceptually similar to computing the entropy of a Euclidean black hole in that gravity theory. So we have some classical solution, and then we do the quantum mechanics around that classical solution. So in Euclidean gravity, we can well, maybe I should emphasize. So let me make a small parenthesis here. So in Euclidean gravity, we can take Euclidean time to be a circle of length beta, and then there is a Euclidean black hole solution which roughly has a shape like this, where this is the radial direction, and the circle shrinks smoothly at r equal to 0, which would be the position of the horizon. And then there might be some extra dimensions like spheres and so on, depending on the type of black hole that we consider. And the Euclidean gravity action on this black hole would give us the leading contribution to the free energy. And then we can consider small fluctuations of the quantum fields around this solution, and that will give us corrections. And that's a way to compute the partition function using gravity, right? And using a situation where the expansion in that, so the expansion parameter would be g Newton. So the first term goes like 1 over g Newton, and then we have order 1 or order g Newton to the various powers. Conceptually, what we did here is somewhat similar. So except that what plays the role of the gravity action is this g and sigma action that we, in this case, was explicitly derived from the microscopic model. Okay. Now, I would like now. How much? Yeah, I started a quarter to, right? Yeah. So I would like now to relate this to black holes a little more explicitly. And in fact, we will argue that this expression here in the blackboard and also, well, the Schwarzian action and so on, actually also hold for the black hole case. So we'll do that by pointing out that for certain types of black holes, we have exactly the same pattern of symmetries. Okay, so we will be considering a class of black holes which also develop a kind of scale invariance. They're also critical systems in some way. And this arises when you have a black hole that has some charge Q, some, for example, electrically charged black holes or magnetically charged black holes. And for such black holes, the mass should be bigger than the charge in order to have a smooth horizon. And when the mass goes close to the charge, so when the mass becomes similar to the charge, the Hawking temperature of those black holes goes to 0, and the geometry develops an interesting shape. So if we have flat space far away, let's say we have a black hole in 4 dimensions. So we have far away, we have an ordinary Minkowski space. And near the black hole, we find a geometry which roughly can be drawn this way. It has a long throat, and the geometry of this throat is AdS2 times S2. Okay. So it develops a long throat. So and then at some point here along this throat, there you have the actual horizon. And so it develops a long region where the geometry is well approximated by AdS2 times S2. So the S2 is just the sphere transverse to the black hole. So this is a spherically symmetric black hole. The S2 is very far away. And when you approach the black hole, it reaches a finite size. And then it keeps that finite size as you go down this throat. That finite size is the area. I mean, that finite size it has here is more or less the same as the one it has here at the horizon. So that finite size is set in the entropy of this black hole. So the entropy will be the area of this S2. And the AdS2 is parameterized by the time direction and the radial direction of these, and the radial direction. Explicitly, I mean, you can say the metric has the form minus dt squared times r squared plus dr squared over r squared. So where very small r is down here and very large r is here. Alternatively, we are going to use these variables. So this is changing r to 1 over r, slightly simpler. So this is the metric of AdS2. And so in this case, let's consider exactly the extremal case. So c equal to infinity is very down this road. So c equal to infinity is when you go in this direction. Okay. And c equal to 0 is when you go in this direction up. But of course, in the black hole case, we don't go all the way to c equal to 0. There is some UV cutoff, if you wish. In the language of AdS-CFT, that would be a UV cutoff. In this language, there is some cutoff near the boundary of AdS2. And there we join to 4-dimensional space. Okay. So if we were to so we have our AdS2 space. There is the time direction, and then there is the c direction. Okay, so I'm just drawing a little plot of this metric. We will have some kind of boundary here where the space joins into 4-dimensional flat space. And here, well, this continues down. Now, one interesting property of AdS2 is that it has an asymptotic symmetry near the boundary. So if we change t to some function of t, and we also change c to some to c times f prime of t, okay? So imagine we do this change of coordinates. This is just a particular change of coordinates, and we put it in this action. Not this action. This metric. Then from the first term we find like an f prime squared, dt squared, right? From the second term we'll find terms like we will find the term which is dc squared times f prime squared, plus terms that have c, dc, right, and so on, right? And then all of this divided by f prime squared times c squared. Okay. Now, if we think of this metric very close to c equal to 0, and we think of let's say dc and dt as being of order 1 quantities, but so this is of higher order than this one's in the small c expansion, then this metric is invariant because these f primes are cancelling. Okay. So this is what we call an asymptotic symmetry. It's not a symmetry of the full metric. In fact, you might wonder whether we could fix this up. I mean, we could change this. We could put here some a of t that depends on some perhaps f or derivatives and so on. We could go to higher orders here, right? So you could imagine you expanding this to higher orders and trying to make the metric invariant, right? Just fixing up the term you got here and so on, going to higher and higher orders. And you can do this exercise. And I should mention that I posted the notes in the wiki, and you can find them there. And there are exercises. And one of the exercises is this one, to expand this and find whether you can fix this up, the coefficient. So you can expand to the next order, and you can fix up some of those, make them 0. But then if you went to the next order, then you cannot do that. So there will be a term that remains in the metric. And that term that remains has the form of the Schwarzian of f. Perhaps not surprising. Okay, so the point is that this metric has this as asymptotic symmetries. So an asymptotic symmetry is a symmetry that is a symmetry very close to equal to 0, but it's not a symmetry everywhere inside. These asymptotic symmetries play an important role in flat space. Even four-dimensional flat space has some asymptotic symmetries, roughly of this kind. Also, ADS3 has similar asymptotic symmetries, and that's how the Virasoro algebra of two-dimensional CFTs is realized. So we have an asymptotic symmetry. And this symmetry in this gravity problem, where we imagine that we are, let's say, fixing the geometry here at the boundary, which is where we are going to join it to flat space, right? So we're going to fix the geometry here at the boundary, which is a geometry that is fixed by this little throat region here. From that point of view, it's a global. It should be viewed as a global symmetry of the ADS gravity problem. So we're going to consider an ADS quantum gravity problem where we integrate over all quantum fields inside ADS, but we're going to fix the geometry and the time coordinate along this boundary, right? So time reparameterizations are just the global symmetry of that theory. And the gauge symmetries are reparameterizations which actually vanish at the boundary, okay? So we should think of this as a global symmetry that has been spontaneously broken, right? Because the metric does not respect the symmetry, and so the metric is spontaneously broken. It's spontaneously breaking the symmetry. So this is similar to what we had when we discussed the SYK model and the valley and all that story, right? So this is the discussion in which we have an exact valley. We have exactly ADS2. This is an exact asymptotic symmetry. Now, one way to think about what this symmetry does is the following. So you could imagine, let's say, in Euclidean space. We are now in Euclidean space for a near extremal black hole when we have a horizon. And in ADS2, near extremal black hole corresponds to the Euclidean disk, or otherwise known as hyperbolic space, sometimes also ahistorically called Euclidean ADS space. So this is just hyperbolic space, and then there is this boundary. So this is the infinite space, and then there is this physical boundary where we will join some other space, will be circle. So that's the simplest configuration. But if we act with these functions, that's equivalent to considering other geometries where the boundary is different. Okay, it has some little wiggles near the boundary. That's roughly because in the new coordinate we have this f prime, and that shifts the position of this cutoff. Okay, and in the exact ADS2 discussion, the action is just simply the integral of square root of GR, which is topological invariant, and so this and that will have exactly the same action. Okay, again, as long as these two curves have the same length. Okay, so that's this valley discussion. And ADS2. So we discussed that these isometries in general are not actual symmetries, but there is a subgroup which is a symmetry, which are the SL2 isometries of ADS2. Those are symmetries of this, and this corresponds to taking this circle and making displacements of these circles, either rotating the circle or displacing this circle inside ADS2, and those preserve the geometry of these cutouts of the interior of this circle. Here, the geometry of the interior is different. It's like you're making a cookie with a cookie cutter, right? This is a perfect circular one, this is not, so you could distinguish that they are different just looking at the interior. Okay. So now we have a familiar situation. So we have a situation where we have a symmetry diff S1 divided by SL2. It's a space of Goldstone bosons of these situations. And then we can say, well, what's the simplest action we could write down, right? So the symmetry is not exact because it's not exact in the physical situation because we don't go to exactly 0 temperature. We go to really low temperatures, but we haven't completely decoupled the ADS2 from the 4-dimensional space. So there will be some influence from this boundary region where, let's say, for example, the size of this sphere has not reached the extremal value, but will be a little bit outside the, a little bit deviated from the extremal value, right? And this will cause some perturbation to these arguments. Okay, so the symmetry will not be exact. What could be the first? Deviation for this symmetry? What could be the action? So the action was independent of f in the extremal approximation, but in the near extremal approximation, the action can only be the Schwarzian. Okay, so it's the same argument for basically the same reasons that we discussed before. Okay, so that's why we presented this argument in this general form. Should be the Schwarzian, and the coefficient. Well, the coefficient will have a 1 over g Newton because it's classical and blah blah blah. So that those aspects are very similar. If you want me to put exactly the right numbers, it's the extremal radius for the black hole cubed. This you just essentially get by dimensional analysis because this has dimensions of 1 over length squared. The whole coefficient here should have dimensions of length, so it should be this factor. Okay, here it looks like we just derive all of this from symmetries, blah blah blah. And you might think this argument is a little vague, but it's a fairly reasonably concrete argument. But even if you are doubtful about this argument, you can actually take the Einstein action and reduce it in this situation and find that indeed you get this term. So this was done in the literature. And knowing that you have this term has some nice applications for finding the low energy dynamics of this black hole. So in particular, suppose that, I erased I wanted to keep it so disorganized. Recall the expression for the free energy that we had and the density of states that we had for SYK, right? That expression with the sinh square root of E and the expression for the free energy that had only a 1 loop correction and so on. Well, those expressions are also valid for black holes, okay? And the reason is that it's basically the same logic. So here in ADS we'll have the gravity problem looks much more complicated. We have this 4-dimensional theory with ADS2 times S2, and we have to compute the let's say the gibbons, just the classic. We're doing a Euclidean black hole, right? So we have the classical action. We'll have all the fluctuations of all quantum fields. These are 4-dimensional fields we would have to do if we want to compute 1 over n corrections or g-Newton corrections to the action. But all those corrections, in the limit that we have exactly ADS2, all they would do is correct the extremal entropy. Okay, and people understand for some theories people can do this to very high orders and even non-perturbatively to compute the gravity corrections to the extremal entropy. All of those would be temperature independent. And then if you ask, well, what will be the first temperature dependent correction? Well, those are the ones we were talking about, and they determine also the density of states. Okay. Yes. No, not at, well. It's yeah. Well, in principle, why not? So because the symmetries are different. So here there's a very special property that the symmetries have this diffeomorphism. Well, the symmetry group is infinite. If we go to ADS4, ADS5, etc., the symmetry group is finite. So there's finite number of generators, and they are preserved by the ADS solution. So the symmetry is realized more simply. The case that is a bit more similar is the ADS3 case. So in that case, you indeed have an infinite symmetry group, which is the Virasoro group. It's also spontaneously broken, and in that case, there is an action somewhat similar, except that it's conformal invariant. It's somehow this Liouville action, which is an action that governs the stress tensor correlators. So the theory that describes those Goldstone modes is basically those Goldstone modes are described by the stress tensor in the CFT and all insertions of stress tensors, arbitrary powers, etc. So that is which is something we normally use to analyze two-dimensional CFTs. So in that sense, it's similar. So one sense in which it's different is that in ADS2 or nearly ADS2, the Schwarzian action is violating the scaling symmetry of ADS2. In ADS3, it's not. And also, in ADS2, it's a little more universal. So some of the physics that we get from when we compute some observables, because of the fact that it violates the scaling, there are some special observables that receive contributions only from the Schwarzian, and you have some universal answers that do not depend on whether the bulk theory is stringy or not or whatever. In ADS3, that's not true. Sometimes the stress tensor might compete with other light higher spin currents and so on for certain observables, like let's say chaos-like observables. So in ADS2, the chaos-like observables are all fixed by the Schwarzian, and you have maximal chaos. For ADS3, they have to compete with other things, and you might or might not have maximal chaos. It depends on whether the CFT is truly has an Einstein gravity description or not. In ADS2, that doesn't matter. So those are some of the differences and similarities. Now, I have to say that when I was discussing this ADS4 this charged black hole, I really lied to you for two reasons. Can you tell? The answer actually for the partition function is not given by the Schwarzian for this case. So the thermodynamics, so we said that it was 1 over beta to the 3/2. No. So this term is fine. This term is wrong. The first thing is that we use symmetries, right? So we use symmetries, and this system has more symmetries than let's say SYK and so on. It has an SU2 rotation symmetry, okay? And that SU2 rotation symmetry will lead to new terms that are somewhat similar to the Schwarzian, okay? So that's one small correction, and that could be taken into account, and people have done that, have considered, especially in the case of U1 symmetry, so like SYK models with U1 symmetry, and then there is an extra term, so which maybe I could say a few words about this. So let's say we had a U1 symmetry. The same thing is true for SU2. Then in that case, you can the G will be a complex function that will involve. So the fermions will be in that model. The fermions are complex, and we have a U1 symmetry that rotates one fermion, the fermion psi in one direction, psi star in the other direction. Okay. And then the low energy equations will have a symmetry, and they're changing G to e to the I alpha of t minus I alpha of t1 alpha of t2 times G, okay, of t1 and t2. So in the same way that that we had this reparametrization symmetry, now we have some symmetry where the parameter, which was a constant in the UV theory, the symmetry generating parameter was constant in time, now could be a function of time. Okay, so we have an extra symmetry, and again is spontaneously broken, blah blah blah, same story. And there is an action which will have the form phi dot square. So here again we write the simplest action that is consistent with having a global symmetry of shifts of phi, which is not broken, so that global symmetry is not broken by the original solution. So this is the simplest action. Again, there is an n over j and so on. And when you do the quantum mechanics of this, there is some extra contribution. It could be extra contributions. Here, some factor of beta in the numerator, beta to the 1/2. That's a simple thing. But there is a bigger problem with this, with a black hole like this in nature. So, which is that if it was electrically charged, the electron would want to be pair created. Okay. And so the one-loop partition function will contain the effects of pair creation of the black hole, right? So there will be some imaginary parts and so on here. So those are reasons why this particular discussion doesn't apply to extremely charged black holes in nature. Okay. If you had supersymmetric black holes which are perfectly stable, then there are to these symmetries we discussed, we should add also supersymmetry. And so again, there will be the supersymmetry becomes local, and the same story that we discussed. And again, there instead of Schwarzians, you will have super Schwarzians and so on. And in principle, you could do that. I'm not aware anybody did it for the black holes, for four-dimensional supersymmetric black holes. But they did it, yeah. Okay. How am I doing with time? Okay, so I think I've finished everything I was going to say about SYK. Are there any other questions? Yes?
Could you comment more on 1 over n corrections of the Schwarzian action? And also I'm wondering what role different topologies and the gravity path control might play as corrections.
Good. Okay, yes. I'm not aware of anybody calculating the 1 over n corrections to the Schwarzian action. The arguments I've said allow them. Now there is an interesting story about other topologies. So far we've only discussed the disk topology. Now this issue of topologies becomes relevant when we discuss not quite the SYK model, but something called the JT theory. I didn't discuss what the JT theory is, but the JT theory is the theory that describes a nearly ADS2 spacetime. So it describes ADS2 plus the leading deviation from ADS2. And so it's a two-dimensional gravity theory, which has an action which has the form phi times r minus 2. So this phi, its four-dimensional origin is the deviation from the extremal area. From the point of view of this theory, phi is a Lagrange multiplier that enforces that the metric is exactly ADS2. Okay. Let me be more precise. So when phi enforces that the metric has exactly negative curvature, right, minus 2, and then if you vary the metric, then you'll get some equations for phi also. And then this is in addition to the term that we discussed before, that we get the topological term that has here a phi naught, which this term really gives the extremal entropy. So this is responsible for S0, okay, the extremal entropy. And this term has to do with the near extremal dynamics. It gives rise to the Schwarzian term at the boundary and so on. So if you consider this theory on a disk, you put some boundary here, and then you get on this boundary, you get the Schwarzian action from this theory. But you could also consider other topologies. So you could consider a situation where this disk is joined to a Riemann surface. Okay, something like this. And this could be a constant curvature Riemann surface. And there was a very interesting paper by Sad, Schenker, and Stanford, where they actually did the sum. Okay, they did the sum over all these geometries in JT gravity theory, and computed what the results are. Now, because these are different topologies, so there was the disk that contained a factor of S0, right? And then as we go to other topologies, we'll start getting corrections. So to this thing, we start getting corrections that go like e to the minus, let's say 2s0 and so on, right? So so corrections of this kind. If you think of S0 as n, these are exponentially small corrections in n. So you have this whole set of corrections. And the other, so it's interesting that they found these corrections, but more interesting than that is that they found that this whole sum is equivalent to what you would get in a matrix model. So in a matrix integral. I'm going to discuss matrix integrals. Okay, so we had this C of beta that we were computing, right? And we computed the first order term in S0 in this expansion. But the idea is that all terms are given by E trace of E to the minus beta, let me call it H. So there is some matrix H. And so we are doing a matrix integral with a matrix H, which is a random matrix. This is not the Hamiltonian of SYK. This is just a random matrix of size L by L, and L is roughly E to the S naught. Okay. So we have a matrix of this size, and we are computing this, and we have to specify what the measure is for the matrix integral. So it's basically a matrix integral dm dh with some measure given by some potential, which is a trace of m, trace of b, and the potential is not quite known, but you don't need it to solve the theory. But what you know is that the eigenvalue density for this matrix has the form of the sinh square root of lambda of E. Let me call it E. E is the eigenvalue of the matrix E. So it has this sinh form that we discussed. So that what this is really is a scale limit, or sometimes called double scale limit, of a matrix integral. I'm planning to discuss matrix integrals and planar theories next time. Yeah, so that's the idea. So this implies that this just purely, if you do the quantum gravity of JT theory, is first a solvable theory, and second, it does not have an ordinary gravity dual in terms of an ordinary quantum mechanical dual. Sorry, this 2D gravity theory does not have an ordinary quantum mechanical dual. On the other hand, it has an interpretation in terms of random Hamiltonians. It's like it's not dual to one particular system, but to an average over many systems. So that's a very interesting result, and a very interesting connection, a very interesting solvable, let's say, example of 2D of a gravity theory that has a concrete, this concrete other integral representation. And what it implies for ADS-CFT in general, I think, is very interesting. And should we think always that ADS-CFT or gravity, the gauge gravity duality, should involve random couplings or not? Or in what cases does it involve random couplings? I think it's raising all these questions that we didn't used to do. I mean, we didn't ask before. Any other question? Yep.
We didn't do the disorder average. Yeah, so if we decide not to do the disorder average either in the matrix model or the SYK model, if we still had very large n, I imagine there'd be a lot of self-averaging in the theory.
Yes, yes.
I'm just wondering how much of this holography story would we expect to go through? I mean, yeah. How important is the disorder? I guess. Yeah.
Well, let me see. you can yeah, there are different answers. So there are some calculations that have been done that speak to this question. One again done by Salchenker and Stanford that have to do with basically it's related to taking two copies of the theory and taking just the naive Gaussian average over two copies of the theory, so computing sort of the partition function of SYK. They do it at sort of, they put some time and then they're computing this quantity, which is take the ordinary thermal partition function and analytically continue in time, so it gives you a kind of time evolution, and then they are computing this average over couplings, right? First you take the square and then average over couplings. This is like a two replica type situation, and then they discuss that, well, in the G and sigma, so the G and sigma action exists and so on, and has solutions that can be viewed as connecting the two sides. So solutions where there's a non-trivial correlation between the G of one copy and the other copy. So there is so G in this situation has two indices beyond the time. So it has two times along the two circles, and then an A and B index which can be one or two, right? And so you'll find the G which is 1 and 2 which is non-zero. And so that's a contribution that will be it's suppressed in the expansion by a factor of e to the minus s naught and minus 2s naught compared to the leading answer, and it has some features that you expect in theories with definite couplings. So there is a whole story of the behavior of this function as a function of time for very long times. Okay, this takes us to slightly. So if you so there's a closely connected okay, so let's well, doubting how much detail to give you, but there's a discussion of how this behaves for very long times. So in, let's say, classical black holes and the naive expressions we discussed, this just decays with time exponentially to very low time, very small times. Okay, very small. But in the exact theory, we expect that this decays, and well, for very long times we don't expect it to go to zero, because this is a bunch of oscillatory exponentials, and if you do a long time average, so when you match the energies of the two sides, you get some average thing that is non-zero. Okay, that comes from the discreteness of the energies. So you get this cannot decay all the way to zero. So from unitarity and the discreteness of energies, it cannot decay all the way to zero, but it can be very small. Okay, so it's very small here. So this is roughly, if I remember correctly, e to the twice the entropy, and then this is like e to the once the entropy. Okay. And then furthermore, it was found that so this holds for very extremely long times, and so these times are of the order of 1 over the spacing between the different eigenvalues, the minimal spacing, which is exponential in n. But furthermore, there is a structure here that has to do with the eigenvalue repulsion and so on that we'll discuss next time. We won't discuss this, but we'll discuss what eigenvalue repulsion, which says that in this region there should be a linear growth in time of this curve. And indeed, this type of geometries give you this linear growth in time that basically comes from the fact that when you consider a non-zero G12, there is a zero mode for how you glue these two pieces, and that gives this linear growth in time. So this whole structure here has to do with the discreteness of the spectrum, and so we see that some aspects of this are captured, in particular this ramp is captured by the appearance of new topologies, or something which you could call new topologies. I mean, this you can do in SYK, and they will be G and sigma and new configurations in G and sigma. For general black holes, you also expect such new topologies. Okay, and this is one. I mean, this issue of the decay of these functions, or similarly decays of two-point functions, is one version of the information paradox, where it's a concrete version of the information paradox, where if you take the naive leading gravity solution, this goes down in time forever, right? But in a unitary description, it does not go down. and it is found in these examples and through these ideas that you indeed need new topologies to the idea. Yeah, new topologies could in principle solve this. I mean, they have the right size to solve it because they are these are effects which are exponentially small. So and they've showed that in these cases they actually do so. Well, they solve some aspects of the problem. Like the ramp, I mean, some very clear, definite indications of the discreteness of the spectrum. Any other question? Okay.
Do you think there are lessons to be learned from this story that might apply to pure 3D quantum gravity? A technical similarity is
Yes,
that
yes.
if you do the
Yeah.
the honest computation of the gravitational partition function,
Yeah.
you get a spectrum that is not.
Yeah,
hence
yeah,
it's
yeah.
not
No, that's true.
compatible
Yeah,
with the
yeah.
discrete trace.
Yeah. So yeah, that's right. So I don't know if you are tempted to say that should correspond to an average over random CFTs, right?
CFTs or something. Yeah.
Yeah, I don't know. Maybe it makes sense. I don't know whether it makes sense or not. Whether there is a sense of average, over different CFTs.
Yeah.
We don't have I mean, for quantum mechanics, we have a clear, this notion of taking a Hamiltonian and taking a random Hamiltonian. But yeah, we don't know how to take a random solution of CFT. Yeah.